Guys, I'm Mrityunjay Prasad, and in this video we are going to solve a question using transformation of variables in double integral. So let's get started. So we have our question here as double integral cos y minus x upon y plus x dA, and here the limit r represents the trapezoidal region with these vertices, that is 1 comma 0, 2 comma 0, 0 comma 2, 0 comma 1, and I have coined them as A, B, C and D. And so if we plot a graph with these points, so our basically trapezoidal region is this, where we have 1 comma 0, 2 comma 0, 0 comma 2 and 0 comma 1. So in integration, our main aim is to solve a certain type of equation with the easiest way possible. So herein, our easiest way possible is by doing substitution. And by substitution, I mean we would put y minus x, which is the numerator, equal to say u, and we would put y plus x as, let's say, v. So from this equation, so from 1 and 2, we can easily spot out that our x is equal to v minus u upon 2 and y is equal to v plus u upon 2. We can easily take out both these values just by solving these two equations. If you add equation 1 and 2, what you would get is 2y equal to u plus v. That means y is equal to u plus v upon 2. And similarly, if we substitute the value of y, we can find the value of x, which would come apparently out to be v minus u upon 2. So now we have to write the changed integrating equation, that is the equation with u and v substituted. So that equation will look like I, which is our integration. It is equal to, now herein the region will be in uv plane and not xy plane, as we know we have changed the integrating variable. And then we have Jacobian. We have this j as Jacobian, which we would further solve into cos u upon v and dA. Now u upon v, obviously where you have v y minus x as u, so therefore we have u, and similarly we have v, so cos u upon v. Now in order to since we have changed the we have substituted the variables, we also have to look at the change in the points when the region has changed from xy plane to uv plane. So for that we need to calculate the points in the uv region. So it is simple. So for, like we have 1 comma 0 as our a coordinate, 1 comma 0 as an a coordinate. So for this point in uv plane, we would have minus 1 and 1. How? Again, u is equal to y minus x. So y minus x, that is equal to 0 minus 1, which is equal to minus 1. V is our y plus x, which is equal to 1 plus 0, or 0 plus 1, which is equal to 1. And similarly, we can find for all the points. So the second point is 2 comma 0. This will change to minus 2 comma 2. third point is our 0, 2. This will change to 2, 2. Then our last point is 0, 1, which will again change to 1, 1. Now we would be plotting these points on the UV graph, and it will basically, the graph will basically look like this. Now this is our new region where we have this as our A, B, and this C and D. As you can see here, -1, 1 is A, -1, 1, then -2, 2 B, 2, 2 C, and then 1, 1 D. So from here we can easily see that our V is ranging from 1 to 2. That basically shows that the lower limit of V is 1 and upper limit of V is 2. But again the question arises, what is the limit for U then? For that we have to check this graph out once. So here let's take the line AB. Now what does AB suggest? AB suggests us that y equal to 0, since the line is on x-axis. So now y was actually what? V plus u upon 2. That is equal to V plus U upon 2 equal to 0. This gives us basically V is equal to U is equal to minus V. And let's check one more time. Let's look at this graph, and here we have CD. Now CD gives us the fact that x is equal to 0. That means minus u plus v upon 2 equal to 0. That means u equal to v. From this and this, we come to know the value, the limits of u, which is basically that u is ranging from minus v to v. That is, lower limit as minus v, upper limit as v, and limit of v is, lower limit is 1, upper limit is 2. So we have our limits here. Now comes what was earlier discussed, the Jacobian. Now how to calculate Jacobian? So it's very easy to calculate the Jacobian. It is modulus of xy upon del u upon v, which is basically modulus of determinant of partial derivative of x upon del u upon del v So that is how we will be finding our Jacobian. So after solving for these values, we would be having modulus of basically minus 1 by 2, 1 by 2, 1 by 2. And as you can easily see, what this is actually is mod of minus 1 by 2, which is 1 by 2. So our Jacobian at the end is 1 by 2. So let's again rewrite our integration with, and then we will put all the values in it. Cos u upon v v4. Now we will simply substitute the values, which is equal to integral 1 to 2 minus v to v cos u upon v into Jacobian, which was 1 upon 2 du dv. Now we would be first integrating with respect to u. So we can simply take 1 by 2 out as it is constant and solve for with respect to u. Then we would have sine u by v into v, as differentiation of u by v is basically 1 by v, which means sine u by v upon 1 by v, which is this sine u by v into v dv. Now we would solve this. Sine 1 minus sine of minus 1 into v dv. This gives us as 2 sine 1 v dv, which is equal to, we can take out 2 sine 1 outside as it is a constant, which would give us sine 1 simply, as 2 gets cancelled by this 2. So sine 1 integration of v integral v dv, which is nothing but sine 1 into v square upon 2, and putting the limits. So this would give us sine 1 into 4 upon 2, which is equal to 2 upon 1, which is equal to, at the end, 3 by 2 sine 1, which is our answer for the integration.